Very much for the invitation. It's really a pleasure to be here. So all I will talk about is joint work with Milena Paviniak. And as Tara was saying, I will be talking on the Gromov width of polygon spaces. So this project with Milena started a while ago because in the team, she's actually the expert on Gromov widths, and I was working on these polygon spaces for quite a long time. And so we were chatting and we said, well, why don't we try to compute it? So this is what we could do. And my plan for the talk is I will first introduce what these spaces are and describe a bit the geometry and topology, and then I will briefly introduce the concept of Gromov width and state the results we obtain. So what are polygon spaces? Well, the first way to introduce them is by choosing n real numbers, R1 through Rn in Rn plus. And for each of these numbers, just consider the two spheres in R3 of radius Ri. This is clearly a compact symplectic manifold. It's scalar with the standard symplectic volume form. And so I can consider the product of such spheres equipped with the symplectic form that is given just by the sum of the pullbacks of the volume forms on each of the sphere. And this is still a symplectic manifold, on which the group SO3 of rotations, the group SO3 acts by rotations diagonally on each of the spheres. Okay, if you prefer, you may think of each of these S2 as cojoint orbits, and this then is just the cojoint action. So this action is Hamiltonian, and as moment map to the dual of the Lie algebra of SO3, which I can naturally identify with R3. And then the moment map takes an n tuple of vectors V1 through Vn, this product of spheres, to their sum as vectors in R3. Right? It would be for each of the sphere just the inclusion, and then by linearity, we obtain the sum. Okay? So with this notation, we can wonder what is the structure of the symplectic reduced space. And this is what I call the polygon space. So let me consider the symplectic reduction of this product by SO3 at the zero level set. And this I will, through the talk, denote with MR, and it's what I call polygon space. So a few remarks, comments, and observations. So why do I call it polygon space? Well, if I consider, I'm taking here the zero level set. So saying that n tuple of vectors V1 through Vn sits in the zero level set for this moment map just means that whenever I consider the vectors from in R3 and I sum them, I construct this broken path, then at the nth step, I come back to the starting point. You should imagine this in R3. Okay? So in fact, this space this is the moduli space of all such closed configuration, modulo, translation, and rotations. I need to pull it up, it doesn't go. Right. Okay. Very good. So first, I like to do numerical example. It's it's simple, but nevertheless nice. So let's do first something silly. This is, of course, an empty space because I have an edge which has length 5, and there is no chance that I'm going to close with the others. So this is empty. And this justifies the following definition. So this will always happen when I have a long edge. So I say that an index set I in 1 through n is long if and only if the sum of the Ri for I9 minus the sum of the Rj for j in I complement. If this is positive, I call the set long, and then when I have a set of cardinality 1 long, then the space is empty. And I say that this is short if the complement is long, obviously. Okay. So more interesting examples. For example, let's think of the equilateral foregone. This is non-empty because, of course, I have the square sitting in the space, for example. But in this space, we have also some bad configurations of polygons lying on a line. So I can choose length 1, 1 like this, and length 1 and 1 coming back. And this will, I mean, whenever we have a line configuration, then this will generate a singularity in the quotient because we have the S1 of rotations that is in the isotropy. So we get the singularity. So this also would justify, I hope, the following definition. I say that R is generic if and only if the sum of the Ri for I minus the sum of the remaining ones, if this is never 0 for any index set in 1 through n, then the length vector R is generic. And as I am to write this scalar quantity a lot through the talk, I wish to give it a name. I will call it epsilon I of R. Okay. So now, the polygon space MR is smooth, and it's a smooth scalar manifold. If and only if R is generic. And in this case, it has dimension n minus 3. R is to be integral. I think it's scalar for any choice of generic I, but as I will not mess with the Keller structure, I may just restrict to the symplectic. I think you need to worry if they are integers when you wonder about quantization and this kind of thing. Let me know. Yes. So what else do I want to say about these spaces? Let me see. Okay, so this is a first definition of the polygon spaces, which I believe is very intuitive and geometrical, and I like it a lot. There is also a more general definition of these spaces. It's actually a result of Hausmann and Knudsen. That if we take, if we consider the complex space C2n equipped with the action of the group, let me call it K, U2 times U1n, where this U1n is the torus of diagonal matrices in the unitary group UN, mod out by the diagonal circle in this product. Then the result is that the action of K on C2n is Hamiltonian, and one can obtain the polygon space MR as the quotient of C to n by k at the 0R level set. So I wrote it in this kind of funny way because now I want to remark that it is interesting to perform the symplectic reduction in stages. So if we first consider the quotient by the torus, let me be a bit sloppy on the diagonal circle in here. Right? Then in this case, we obtain the product of CP1s, or if you allow me, the product of spheres. And the residual U2 mod delta action is the SO3 action that I have just described you before. So this part of the picture we have already in full detail in this blackboard, right? But we can also perform the symplectic reduction the other way around and construct, so if we consider the quotient by U2, maybe I will put a quotient sign. Then we have the Grassmannian of two planes in Cn, on which we have a residual U1 to the n action. And this when we perform this quotient, then we obtain the polygon space. Okay, I'm going a little bit fast on this very nice result, but it's actually a very interesting point, this one, I believe. And I wanted to mention also because during the talk I will be concerned with the chambers of regular value where we take our length vector r. And these chambers are exactly in the image for the moment map of the torus U1n on the Grassmannian. So I hope this. Do you have questions? Shall I give more details, less details? Okay. I'm going a bit fast. So in particular, I want to stress a bit that I will have, if I consider the Grassmannian of two planes in Cn, then the image via the moment map for this U1n action will be, by the convexity theorem, some convex polytope that I don't know how to draw. But the important thing is that the walls in this polytope will have equation epsilon I of r equal to 0. So every wall is associated to an index set I, where the scalar quantity that I have down there is vanishing. Okay. And so to identify a chamber in this moment polytope, all I need to say is what are, if I take a r sitting in here, the chamber C in which R is sitting is uniquely determined by the collection of R short sets. And in fact, more is true. It's enough to tell you which are the short sets that are not contained in any other short sets, because those will be associated to these, to what I call the effective walls of the chamber. So the walls that in fact lie in the closure of the chamber. Okay, the others will follow. Can I use these blackboards, or you don't see them well? Maybe not. Okay. Okay, so another couple of remarks that I want to do are the following. So MR is diffeomorphic to any rescaling M lambda R for lambda positive integer, but of course it's not symplectomorphic. I am rescaling the symplectic form. But what's more relevant for us is that MR is symplectomorphic to M sigma R for every permutation of the n edges. Okay, and this will play actually a crucial role in the way we compute the Gromov widths of these polygon spaces, because we want to use different Hamiltonian systems on these polygon spaces. So we reshuffle the edges until we find one that does the job that we want. Okay. So one final thing about polygon spaces, as I was saying, I want to we will make much use in the computation of the Gromov widths of some Hamiltonian system on these polygon spaces. And that can be defined, I will define first it a bit hand-wavingly by drawing a polygon. So let's consider this polygon V1, V2, V3, etc., Vn. So if I consider the, let's say, the first diagonal that goes from the first vertex to the third, D1, then I can define an S1 action that bends the edges V1 and V2 around the D1 diagonal and leaves the other fixed. Okay, so this defines an S1 action on the polygon space in good situation, which I will comment in a moment. I can also choose the second diagonal and play the same game. I rotate the V1, V2, V3 around the diagonal and leave the rest fixed. Okay, the drawing might be not the most accurate, but I can keep going for as many diagonal as I can find. So this is to give a geometric intuition of what is the bending action, and the statement is that for any system of n minus 3 non-intersecting and non-vanishing, this is important, diagonals, then we define in this way an action of a n minus 3 torus on our polygon space, MR. When some of the diagonal vanish, like if we have, if the R is chosen such that we have a butterfly configuration like this, V1, V2, V3, V4, V5, V6, then we have to take out these points in which the action would not be defined. And then we can only define the bending action on an open dense subset, which I call M, well, M naught of R. Open and dense. Okay. So this system is very nice, has been used, studied in detail by Hausmann and Knudson that I have cited before. And I will use it a lot later. I will give some more details in the case of the polygon when we can draw nicely the pictures. Okay. So I guess I will erase. What?
For certain choices of parameter R,
yeah.
is this a genuine fork action?
Yes. Yes. precisely when you cannot have a, yeah. For example, in the case of the 5 gons, this is easier to give really numerical example, 1, 2, 3, 4, 5, because it's sufficient that you require that R1 is different from R2, so this diagonal D1 will not vanish, and R4 is different from R5, so the last diagonal will not vanish, and then you're guaranteed you have a good toric action. For a higher number of edges, it's a bit more, you have more variables. So, Gromov width. So I'm sure that I'm really not an expert. The little I've learned, I've been enjoying a lot in this last period with Milena. She taught me all I know. And as far as I understand, the idea of Gromov width is to understand essentially how big you can make your Darboux chart inside your symplectic manifold, somehow. And it originates with the work of Gromov, the famous non-squeezing Gromov theorem, that tells you that if you wish to embed a ball of radius r inside a cylinder, like this, where here you have a capital R, so this is B2R times R2n minus 2, and this is, let me get the dimension right, B2n R. So if you wish to have this as a symplectic embedding, then you can have it only when small r is smaller or equal than r, and in fact the embedding is the one you would think you put your ball here somehow. Okay, so with this example in mind, I want to define the ball B2NA, ball of capacity A, as the Z in Cn, such that pi times the sum of the Zi squared for I is smaller than A. This is an open ball. And I want to equip it with the standard symplectic form that it inherits from Cn. Okay, then given any symplectic manifold M omega, the Gromov width of M is defined to be this. So I will try G of M is the supremum of the A, such that the ball of capacity A can be symplectically embedded in M. I'm trying to switch my notation for the Gromov width to this G. Sometimes I may write GW by mistake. I never speak of Gromov width and invariance. I'm always on the Gromov width. They told me that GW is not a good notation, so I'm trying to switch. Yeah. So, yep, let me pull this up. So as far as I know, the Gromov width of symplectic manifold is known in only few cases. There are some results on lower bound and upper bounds, but a sharp result on the Gromov width is not known in much cases. there is a work of Carchon and Tolman where they compute the Gromov width of the complex Grassmannian. And there's a work of Lu when you give some results for the Gromov width of toric manifolds. And what it means by some results is that it gives some lower bound and some upper bound, but very often there is a gap in between the two, so we don't get the full. And then there are works of the student of Tara, Milena Pabiniak, and Javier Descastro. I mean, the works are separate. I will. Milena works on the lower bounds, and Javier Descastro works on the upper bound, but together they compute the Gromov width for some coadjoint orbits. Okay. So correct me if I'm wrong, I may, but I think there are not many other examples of which the Gromov width is really known. And what we do with Milena is compute the Gromov width for these polygon spaces. So unfortunately, we don't have good results in any dimension. So I will write right away the results, all the results we have, and then I will comment on this. So the first things of myself and Milena to come is that if R is, so let me assume, I'll put it here, R is generic. Don't, I may forget to write it, but I'm only dealing with most manifolds, so R is always generic for me. If R is generic, 5 gons, R5 plus. Then the Gromov width of MR is 2 pi minimum between 2Ri and the sum of the Ri minus Rj for I different from j. This for every j that goes from 1 to 5. Okay, so for the 5 gon, we have really the Gromov width in all the cases. In this case, the polygon space is 4-dimensional. And then for the 6 gon, it's already a bit more annoying. So myself and Milena, we have that the lower bound is always that. So we still take R generic. The Gromov width of MR is bigger or equal than 2 pi times the minimum between 2 Ri and that sum. And now for j. Okay, but unfortunately for the, sorry. I'm continuing the theorem from there, so that is for the lower bound. For the upper bound, we are in trouble. We don't have good upper bound for all, so if, let's consider, let sigma be a permutation on the 6 edges, such that R sigma 1 is smaller than R sigma 2, etc., or equal eventually. So we are reordering the edges in this increasing way. Then if R sigma 3 plus R sigma 4 plus R sigma 5 is smaller than R sigma 1 plus R sigma 2 plus R sigma 6, then what we wish. So then we have that the Gromov width of MR is also smaller or equal than 2 pi, the minimum of what is above. Okay. So this condition may sound a bit awkward. What it's saying is that we are able to have sharp upper bounds for chambers that are external enough. When we cross many walls and we go deeper inside this moment polytope, then the manifold is not Fano, not a blow-up of a Fano manifold, and we are not able to, we don't have techniques to have a good upper bound. Okay. And then there is a last result. Still together with Milena is everything. So if now we take R in Rn plus generic, so I'm doing the n-dimensional case. I assume that assume that there is an index set of cardinality 1, I, that is maximal short. So I itself is short, so the moduli space is not empty. But as soon as I put another j, it becomes long. Okay? Then the polygon space MR is symplectomorphic to CPn-3 equipped with a multiple of the Fubini-Studi metric, where this metric, sorry, symplectic form, I got confused. But this multiple is exactly R1, so it's the sum, now I call I call it J, because now I want to write again the sum of the Ri minus Rj for I different from J. And this is precisely that one. Maybe there is a 2 that I'm... Yes, I am in a chamber that contains in its closure a vertex. I'm in a chamber like that. So note that in particular, if this is the case, if J is maximal short, then you can, if you wish to consider the same collection, so the minimum of 2 Ri and all those possible differences, then under this assumption, you get that this is the minimum. So it fits with the pattern that we have above. It's one specific case, but it does fit with it. I believe I have a 2 here. Sorry, I didn't double check, but I really trust. There's a 2. Okay. So I want to use the second part of the talk to try to give idea and details of on how we prove these results. But I want to spend here a minute to say that to us it seems that really it should be, we should be able to conjecture that the Gromov width of polygon spaces is always that. I don't know if really to call it conjecture or expectation or whatever, but we think that if R is generic, then the Gromov width of MR is going to be exactly 2 pi, the minimum, the Ri, twice Ri, and that sum. And one thing that we would be really interested in knowing, and we don't find it in the literature, nor we are able to prove it, is that if you start from, if you do symplectic cut, so you start off with a manifold for which you have an upper bound for your Gromov width, and you do symplectic cut to this manifold, then can the Gromov width increase? We would expect not. We would expect that the Gromov width can either stay or decrease, but yeah, if one can prove this, then I think we can prove our conjecture. Okay, so I will spend most of the time on the 5-gon case. I will erase here. Save it. Okay, so as far as I know, when one wishes to compute the Gromov width of some symplectic manifold, the lower bound are determined by some equivariant techniques, for which I will use our bending action. And the upper bound is the one that is more tricky, both for me and for Mila, because we are not expert on J-holomorphic curves and this kind of thing. So we will use here some results of Guan-Kun Lu. I guess one can hope to improve his result also and prove that. We are so far not able. So I have been thinking a bit how to do it, and I will do it with examples. I know that the proof by examples are not the most rigorous, but okay. So when we have the bending action for 4 gons, 5 gons, sorry, I don't know what is it. So as I was saying before, following the question, when we have a 5 gon and we want to consider the bending action, it's enough to guarantee that R1 and R is different from R2 and R4 different from R5 to have the action. And in fact, D5, D1, D2. So let me assume for a moment, I will drop this assumption very soon, that this is the case. And R4 is different from R5. Then the action of T2 on MR is toric. And as with moment map, the following moment map image effect. So what we do is very simple. For the bending action, there are action angle coordinates, and the action coordinates is the length of the diagonal around which we are bending. So our moment map will just take a polygon to the length of the diagonal D1, comma length of the diagonal D2. So what will be the moment image? Well, we must consider all possible lengths for D1 and D2 such that the triangles of edges V1, V2, and D1, D1, V3, D2, and D2, V4, and V5, they all exist. We want these 3 triangles to be there. And if you work out the triangle inequalities, this tells you that your D1 and D2 must lie in the intersection So of this unbounded region here, this is y equal to x minus R3, y equal to x plus R3, and this here is y equal to minus x plus R3. And the rectangular region where here I have absolute value of R2 minus R1, R2 plus R1, R5 plus R4, and absolute value of R5 minus R4. Okay, and the intersection of these two is the moment map image. Okay, so I have here an example that I wanted to. So for the lower bound, what we do is we look at the moment polytope and we search for a sphere, which means we'll search for a simplex, thanks to what I now know is called the trainer trick. So let's do it in one numerical example. I want to choose. I have prepared this example because it's simple, but bad enough. So this one is bad because it's non-toric, 2, 2, 4, 4, non-toric, but it's still smooth. And precisely, it lies in a chamber that I call C5, just because it's C5 in our paper, that is determined by the following short sets. So we have 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 1, 2, 3. I may need to comment on the short set later, so I'll keep that aside. Okay, non-toric, bad. So we reshuffle. Maybe it's spelled correctly, I'm not sure. I probably erased it, but when you apply a permutation on the order of the edges, the manifolds are symplectomorphic. So I want to shuffle it to, say, R tilde equal to 2, 4, 4, 2, 3. Okay, now this is historic, so I can draw the moment image. And for the moment image we obtained, so now we have 4. The difference is 2. The sum is 6. The difference is 1. And the sum is 5. So the square is something like this. And the intersection is this. So after a little bit of playing with these polygons, I can tell by looking at the short set that I expect the Gromov width to be twice the minimum of the R's, that this is not the case, because this case occurs only when I have a maximal short index set of cardinality 1. So here I have none. Of course, I always have the I, all of them. But anyway, so my expectation for the Gromov width is that it will be 2 pi, well, yeah, 2 pi times 2 R 1, yes. So I want it to be 2 times.
Sorry, your expectation is that you only get that time when you're in the outer chamber. Otherwise, you get twice one of the RIs. Is that what you just said?
Yes. So actually, this is actually what is written in the Blackboard. I haven't worked it out. So if you check what is the minimum between this The minimum is this second component only if you have that I is a maximal short sets. Otherwise, it will only be one of the others. Okay.
Sure. Right.
Yeah. So with this numerics, I think I'm looking for a ball of size 4. And I maybe see it, let me see, here, and here I can fit a diamond. So now I use this example to discuss a bit how we embed balls into our moment polytopes. So through the paper, we always use the results of Schlenk, McDuff, and sorry, I hate when I forget the name. Yes, thanks, Latro. I hate when I forget the name of one of the authors. It's really bad. Thanks. So maybe I will use my note anyway. I didn't bring it, never mind. So what I want to do is, the first guess is to try to look for a simplex. And I'm claiming that whenever you find a simplex in your moment map image, then this means that your symplectic manifold fits a ball. And without going into the detail of the trainer tricks, I hope to so what I want to say is that, for example, if you consider the Tn action on C to n, which is kind of our model picture, then the moment map for this action will take Z1 through Zn to a half norm of the 1 squared, etc., norm of the n squared. And then a ball of capacity A in here would be mapped to the simplex, right? Well, I've drawn this dimensional simplex, but the appropriate one. So in a way, this tells you that locally, when you find a simplex, you should expect to have a ball embedded in your symplectic manifold, or if either really you find the ball fitting, or you do some tricks. And Schlenk. So I copied the name because I want to have them written on the blackboard, as I really do so many tricks to find embedded balls, and it's really important to us. McDuff and Schlenk. This is our source of drawings. They show that not only you can embed a simplex, but if you can find a diamond, which is you fit a cross of size A, actually 2A maybe. Then if you're worried as us about a toric manifold, if you fit the cross, you know that also the convex hull of the cross will sit in your image. So if you have this in your moment image of, I call it mu r because it's what I care, then you know that you can fit a ball in the image, in the pre-image, which is the diamond times the torus. They give details. And there are also more complicated construction, like shearing. We luckily don't use them in the polygon space, but I wish to mention them. Okay, so for this we find that. What do we do about the upper bound?
So you just use the standard criteria?
Yes. Yes. Even in the six-gon case that hopefully I will get to mention, we still use a diamond. We show that we can fit 3 axes meeting at a vertex.
In the 5-gon, in this particular 5-gon case, it's a diamond, but in all the 5-gon cases, it's a diamond.
Yes, in all the, not even distorted, always a diamond. Yeah. I mean, it can be a diamond where that goes like this, so yes, distorted, I'm sorry, but not sheared. This is as bad as it gets for polygon spaces. Even in the 6-gon. That is the situation with an extra axis coming up. So I'll write here, I guess. So for the upper bounds, the result that we use is the following theorem by Lu that says that, so let me consider the Delzant polytope delta, which is given by the intersection of these hyperplanes, so x in R, and such that x times ui, well, not times, it's bigger or equal than lambda I, delta Delzant. Okay, let x delta be the smooth toric symplectic manifold associated to smooth toric symplectic manifold associated to delta via the Delzant construction as usual. Then, and this is really crucial to us, if x delta is Fano, then the Gromov width of x delta is, I think I mean symplectic Fano. I mean that I don't want this shape in the moment polytope. Yeah. Is smaller or equal, I will comment a bit on that example. Then the infimum of the sum of 2 pi lambda k ak positive, sorry for the ak uk equal to 0, and where these ak are positive integers. Okay, written down the theorem, very good. What does it mean? It means something very simple, in fact. It means that you take your moment polytope, let's do it here, check for the inwards pointing normal. I erased to have some. Okay, like here. And you want to look for a combination of the UIs such that there's some vanish, and then you compute the scalar quantity. But this is not good because it's not Fano. And we can see that it's not Fano because we have this shape here. So we cannot find a monotone polytope with the same normals as I have here. I don't know what is your favorite way of checking this kind of things. But still, the problem can be easily refixed by reshuffling again in a more clever way. Let me get to them. Positive integers, yeah. Or 0, yeah. So this is not actually the worst case scenario if taken a rather mild one. But if we reshuffle in a clever way, we take 2, 4, 2, 3, 4. Then we have changed chamber in the moment polytope associated to the Grassmannian, but our symplectic manifolds, the polygon spaces, are still symplectomorphic. And for this reshuffling, I obtained that the moment image is now, so we'll have 2, and then it will be something like this. No. Okay. So this is my new moment image, which is very good. It's still toric. Now it's Fano. I can apply Lou theorem and obtain. So it will only tell you that I consider these two normals. And if you believe me, the scalar quantity that he has there, so the, what is it, lambda k, ak, I believe, is equal now to 2 R1 for this choice. You need to keep track of what your, yeah, there's a 2 pi that I'm missing. Anyway, so this maybe it's worth writing. This will be now with my reshuffling 6, and this will be 2. So in fact, here I will get something of length 4. If you, it's actually, I'm sorry, I've lost track of the, but you can do it a bit carefully. So this is R1, this was R4, R2, R3, and R5. And if you do it with this reshuffling of the length, assuming that, well, with those short sets for the original R, then you will obtain 2R1. Okay, I have 5 minutes to sum up things. So essentially, this is what we do in most of the cases of the 5 gons, where we can prove that, I mean, first we check if it's toric. If not, we can see if by reshuffling we can obtain a symplectomorphic toric one, and if it's Fano, and then we apply these two techniques. These are the very good cases. There are some bad ones. For example, the equilateral polygon space, which is of much interest to many people, especially to algebraic geometers. I haven't mentioned, but these polygon spaces also occurs as quiver varieties, and also as moduli of parabolic bundles. So, and in those settings, the equilateral case assume much interest as far. So the equilateral case M1, 1, 1, 1, 1 is not toric. It's smooth, but not toric. And with not toric, I mean that not only I cannot make it toric with the bending action, it's really non-toric. Hausmann and Knudsen prove that they computed some topological invariant. I think the Riemann-Roch number and the Euler characteristics, and they have different numbers. And so this is really non-toric. And for this case, we followed Dominique Joy's suggestions to use continuity, because and so what we do is we study I go back to the R notation, so we do R plus T, R plus T. So for this equilateral case, we have a path going through it of smooth toric polygon spaces. And then we can show that the upper bound for the Gromov width of MT, this one, is, so this is, we know by Zo's technique, that is 2 pi times 2r. And we show that this is also an upper bound for the Gromov width of M0 by using some variation of the Moser trick. We solved that, yeah. And so for the upper bound, we use this continuous technique. If you wish, I can give you more detail. And for the lower bound, we see that this is not toric, but we can consider the action of the two torus on the open dense subset R, where we have thrown away essentially the points where, in fact, the diagonal vanish. And then for this, I mean, you get something like this. You can think it as a limit moment image or as a map for as the image for the continuous map that maps to the length. It's something like this with open here. And then you can still fit the ball in here with the techniques I have described before. And as the Gromov width is defined as the supremum, we are fine if we can fit open balls. So we can fix this problem. So final remarks. I will do only one because I don't have time. So for the proof of the projective space in any dimension, it just boils down to recognizing the correct symplectic form that we have here, and then that the Gromov width will be precisely this. It comes because it's a projective space. And for the sixth-gon, we have to use a different system of diagonals. I'll write it here. We have to use 1, 2, 3, 4, 5, 6 diagonals as follows. Okay. Because the other system of diagonals give us, it gets much more, we are not able to find lower bounds with the other system. And with this, we obtain again, we have a cube chopped out by some hyperplanes, and how much is chopped, it depends on the choice of your length. So we do the same thing. So this is all. Thanks a lot.